Hello, my name is Charlie Maslin, and this is my presentation on an automated platform for microrobot manipulation, which is research done at the University of Chemistry and Technology in Prague. The development of microrobotic systems that can perform useful work promises to advance technologies in a wide variety of fields, just as conventional, human-scale robotics has transformed all industries in modern society. They can reach previously inaccessible length scales for sensing, manipulation, and delivery. Additionally, actively moving microrobots can overcome diffusive mass transport in aqueous environments. As such, the in-field applications of locomoting microrobots can include pollutant degradation removal, bacteria killing, or dynamic environmental monitoring. Moreover, they can gather and report on the chemical composition of its surrounding and serve as an autonomous mobile microsensor. In this work, we have developed crawling microrobots and an automated system for their manipulation and navigation. From the video above, you can see our microrobots are 100 micrometer diameter discs composed of a soft material. This is a photoresponsive hydrogel for which pulses of focused laser light induce a localized shrinking swelling response. The hydrogel is a cross-linked network of the thermally responsive polymer polyanisopropyl polyacrylamide. By incorporating gold nanoparticles within the structure of the gel, the thermal response can be tuned into a light-induced response, for which laser light of 532 nanometers can locally heat the gel and cause it to shrink. Owing to a hysteresis in the friction between the hydrogel and the surface, off-center actuation leads them to displace in the direction away from the beam. This is the reason we have chosen discs, as they have full translational and rotational freedom. The production method, stop-flow lithography, is relatively simple and allows us to produce tens of thousands of microrobots during a 1-hour synthesis. The automated platform we have developed consists of a microscope on which is mounted a fixed laser. Instead of moving the laser, we move the stage that holds the sample of microrobots, which is achieved by an XY platform attached to 2 stepper motors. The NAMA 17 step motors are controlled by a Raspberry Pi 4 and driven with TB6600 drivers in quarter microstepping mode. The quarter microstepping mode, combined with the micrometric bolts of the XY platform, allow precise precisioning. Approximately 6 steps are required to change the location in the image by 1 pixel in the desired axis, and this resolution is the same for both axes. This is sufficient for manual control. However, for automated control, we have developed an image recognition and control system that automatically positions the platform to achieve a desired movement of the microrobot. Image recognition software is used to localize and register the position of disks, and the user can select a disk in the sample and set a target location. A control algorithm is then used to determine the subsequent movements of the XY platform and the laser pulsing, such that the microrobot is driven to the target. The localization of the disks in the images is achieved by use of a normalized correlation coefficient algorithm, which we find has a 95% success rate of detection. The algorithm can be summarized by the following steps. Firstly, the normalized correlation coefficient is estimated for the first template. If this is higher than a threshold value of 0.7, then the disk has been recognized and the coordinates of its center are stored. The area of the disk is then replaced with the average background color, and this process is repeated for all templates. All of this image processing is done using NumPy and OpenCV libraries. The results are as follows. On the left, you can see the registered disks and the pixel coordinates of their centers, and on the right, you can see the image after all disks have been registered and replaced by the background to avoid repeat detections. To control the disk, the user must first manually set the coordinates of the laser in the software, which remain fixed with respect to the camera. The user may then select the coordinates of a target position. The software will then localize all disks and allows the user to select which disk is to be controlled. Each disk has 8 different regions for illumination on its body that correspond to 8 directions of travel, shown on the above right. With a disk selected, the stage is moved into the desired position for illumination, with the position of the laser at the illumination region which will provide the greatest displacement towards the goal. The laser is then pulsed such that the disc displaces towards the goal. The coordinates of the target are then recomputed based on the change in the XY platform, and the process is repeated until the center of the disc is within 5 pixels of its target. The user interface during the working mode can be seen now. The user can first check that all the camera conditions and illumination is correct by searching for all discs in the sample. They can then set a target for which a Microrobot will navigate to. They must then check that the laser is calibrated with respect to the camera. And then finally they can select a disc from the sample. After doing these, the algorithm can then be left to run until the disc navigates to its destination. This Python-based software and user interface was developed, and the main functions are camera settings, image processing, laser camera calibration, setting the goal, template for pattern matching acquisition, and saving the images and creating video sequences. The user interface was created using PyQt and a framework that enables the portability between Windows and Linux machines. The performance of the system is shown here now sped up. The black star is the target position, and the localized position coordinates of the disk centers can also be seen. It is worth repeating that the Microrobots are moving over the surface, but with their positions essentially fixed with respect to the camera, due to the laser being fixed with respect to the camera. In future, we would like to improve the disk localization algorithm and enable it to recognize multiple shapes that would enable extra functions such as grabbing and steering. Furthermore, we would like to include a path planning algorithm for the disks to navigate in environments containing obstacles. This feature is necessary to then assemble disks into predefined complex arrangements. With that, I'd like to acknowledge the following fundings, and I would like to thank you for your time and for listening.